Good morning and most welcome to Visual Forum 2011. I'm Monica.
And I'm Andreas.
From Center of Visualization. And we are very sorry for this delay in the morning with the lights out. And we will be a few minutes late during the day now, I think, for like 5 minutes, because we start a little bit later. So I just want to say that today we have parallel sessions in the morning and parallel sessions in the afternoon. This morning it will be gaming and visualization for health and medicine and 3D scanning and data capturing. And there is one more session that's not in the program, but you do have it on the back of your badges. And that is a workshop, which it will be in Tesla. So, and I think Andreas wants to say something very fun.
Yes, and we just want to take the opportunity here today to mention for all of you that haven't heard it so far that we have been working several years now to establish a new visualization center here at Lindholmen. And last week, Wednesday, the city of Gothenburg decided to put in 15 million Swedish crowns into that project. So it's really good news, and maybe in about 8 months or so, we can open up this center just next door from here. So we think it's a really, really good news that we want to share with all you.
Okay, so now we will welcome up Staffan Trevé. Give us an introduction.
Welcome, good morning. I think the organizers did a great job this morning of showing how important vision and light is by giving us this dark room to come into. You couldn't see a thing. So I wanted to say a few introductory words about visualizing the future, which you've seen is the theme of this year's Visual Forum. So therefore, this starting picture. I think this is one of the first cases of visualization which we know of, which actually proves that visualization is actually one of the oldest human technologies of all, as you can see. And the interesting thing is that if we believe the anthropologists, it's actually the case that the reason these cave paintings were made were actually for visualizing the future. Because the guys sitting there painting them were actually talking about when they were going to go out hunting, and they wanted to describe to each other what the hunt would be like, what they would be doing, and so on. And ever since then, we've used visualization to actually help tell each other about how we think the future might look. Pretty amazing, isn't it? 17,000 years ago, and we're still doing it. So, you know, going up in history, some great examples from back when as well. Leonardo da Vinci's paintings and drawings is also an excellent example of how you use visualization as a way of describing a new idea to an audience who might otherwise have a very hard time understanding it. One of my favorite examples is on the right here, a Frenchman, Albert Robida, who in the mid-1800s had some great ideas about the future. Here's one of his examples, the telephonoscope, which was a device where you could actually sit at home and look at the theater without having to go there. Pretty interesting, right? More than 130 years ago. And he also had an idea that not only could you do that, you could also have this telephonoscope connected to the clothes stores. So instead of going to the store to buy your clothes, you could sit at home and watch what the clothes looked like. And then you could click on something and buy them. So, you know, pretty foresighted guy. And he also used text, but also these pictures to convey his ideas. And, you know, it's been like that ever since. And going forward, well, Jetsons, you all seen that and so on. So the interesting thing is that in essence, we're doing the same thing today, of course, with much more heavy-duty technology. So today, when we're deciding to build a new building, for example, of course, we use visualization as a way to both understand what it's going to look like, but also very much as a tool for telling people and decision makers and so on what it's going to be. So someone who has a complex idea can, in terms of a simple visualization, convey these ideas. It's extremely powerful, really. Same thing, of course, if you're developing products. This is a bit hard to see on this projector. So, you know, the building there, everyone understands that the technology exists to do it. But of course, visualization allows us to also describe things which are not quite doable yet. So if you have this case where you have a kitchen shelf like this with some tomatoes, but this is special, so you can actually press down your hand like that to make a bowl in the shelf. Pretty neat idea. Very hard to do in reality right now, but maybe in a few years. So visualization is a good way to describe that. And of course, you can mix your salad straight in the shelf like that. Great idea, good way to describe it. You know, if you wrote this in words, it would not be as captivating as it is now. And of course, I think the master people in terms of visualizing the future is Hollywood, of course. You know, all the movies we see and the effects they do there is really a way of describing possible ideas about what the future might look like. So again, this theme that we convey is a complex idea through simple visualizations. So all these things are really visualizing the physical world as it looks. But I think one of the things we haven't been able to do so far is really to visualize information about the future. So if we look at what we do in information visualization today, we can do great things to describe global heating or demographic changes in a culture, or we can go in and take data from chat rooms and so on and create wonderful graphs like this to see who is talking about what and so on. Excellent ways of visualizing information. But as a matter of fact, oops, sorry. That one disappeared. The thing is, we're always looking in the rear mirror. So information visualization has very much been a question of looking in the rear mirror, seeing things which have happened in the past. And I think that's the next challenge, really, to see how can we start visualizing what's going to happen in the future in terms of information. And if you look at it, we're actually getting better at understanding the future. We've been doing weather projections for about 150 years now, and they're steadily getting better. Everyone complains about them, but still, today we can reliably predict the weather maybe a couple of days into the future. And of course, we see visualizations every day when we look at the weather maps. And we have other things like, trains will be arriving in 1 minute, 200 miles before you need to go to the garage with your car to change oil and so on. So we're starting to peek into the future in small domains. So the company I work for right now, called Recorded Future, what we thought was that there must be more to this. There must be more ways we can look into the future. So what we've been starting to do is to see, can we harvest the information which is out there on the net in terms of future? And if you start looking at text, it's ridiculous. Maybe your mind gets obsessed, and that's why you see it that way. But almost every sentence, when you start looking at it, says something about time. And an interesting fact when you start looking at this, there's some time here. When you start looking at this, is that something like 4 or 5% of everything which people write on the net is actually about the future. It could be someone twittering that I'm going to go down to the shop and buy milk in 5 minutes, or it could be someone saying that the weather in England will be much worse 100 years from now. But anyways, 5% of all the stuff that's written there is actually part of the future. So the project we're working on right now is to actually take all this information, the unstructured text, and create analyzable data out of that. So I'll just give one single picture as an example. So, what we can do then, we can create nice timelines. So this, which looks like a mountain with some clouds, is actually a visualization of Apple's product release news for 2011. So of course, being here in early May, we can see that most of the news is actually about the past. So, and you can see these curves here, which is a momentum curve describing how much talk there was about things. Green is good news, red is bad news. The cloud there is actually the individual events, which you can see up there. So you get the feeling that clearly there was something important happening in March, which everyone now knows was the iPad 2 release. The first good news and then some bad news. I'm not sure exactly what that was. But the interesting thing, again, if you look down the year, there is actually quite a bit of news about the future as well. And we can see these. Of course, the farther we go into the distance, the less information you have. But for example, you have information saying that iPhone 5 will probably be released sometime in September. Now, of course, anyone can say that we're not really visualizing the future here. We're visualizing what people think about the future. But I think that's actually, in many cases, good enough. If you look at the financial world, for example, the only thing people care about is not what's going to happen, it's what people think will happen. You get the difference, right? Because price of things, for example, is driven by expectations, not by the actual future, whatever that could be. So what we've been doing now for a couple of years is really working on creating huge data sets which describe both the past and what people think about the future. And I think the big challenge is to find good ways of visualizing that. Very much a question of not just showing the raw data, but finding adequate ways to aggregate data in ways so that you can actually, again, convey ideas about the future. In this case, it's not a single individual. It's really an aggregated view about what anyone who's active on the web is thinking about the future. So, this was my little introduction. I think you'll see a lot of really futuristic stuff at the conference here and in the presentations and so on. I think you should all focus also on interacting with each other and talk about how we can use visualization not only for the benefit of the future of visualization as such, but really to understand what's going to happen in the future. Have a good conference.
Thank you very much, Staffan. Thank you for that introductional speak. Now it's time for the first parallel session, and in this room we're going to continue now with 3D scanning and data capturing. For those of you who want to listen to the gaming and visualization for health and medicine, that's going to take place in the room called Pascal. It's down the hallway and then to the right. And for those of you who want to go to the workshop in 3D workflow, that's going to be in the hall of Tesla. And we start the next sessions in about 5 minutes. Thank you.
We will have 3 presentations, and the first presentations is from Mr. Rolf Berlin and David Johansson. Rolf is the founder of ATS, Advanced Technology Solutions, and they're going to give the speech now on high-resolution color 3D scanning of industrial environments and city buildings. Please welcome Rolf and David.
So, hello. Yes. Just starting up, we have a little 1 second, and then we'll start up.
All right, then I can tell you that we have these three talks will be given each 20 minutes, and we will have questions after each talk. And a suggestion is also to have a final sum up during the coffee break. We can all gather down in the end corner by the round tables if there will be any discussions or need to have further conversation with the speakers.
Kan du se om du får igång det här? So, all right. Now, we will talk about a new technology about 3D scanning, color scanning, and high resolution. 3D scanning has existed for about 15 years, roughly, and has been developing rapidly the last 5 years. So there has been several paradigm shifts the last few years where you can use the data in a completely new way. And that's what we want to show you today. It's not this that you're loading down your software, you cannot move, you cannot see anything. Things has happened rapidly in those areas now. So what is 3D scanning? We look here now at the scan cloud of a sculpture, and it's captured of a machine like the one I have here. It has a laser transmitter and receiver looking at in a 45 degrees angled mirror, and the mirror rotates, giving you a circle of points. You are measuring with up to 1 million points per second. And for example, the resolution could be 10,000 points in one turn. And that means that if you then rotate the house 180 degrees, you will get a complete sphere of points around you, covering everything. And on a distance of, let's say, 2 meters, you will have a point in every square millimeter. And that is high resolution scanning. Accuracy, some millimeter. You can measure up to, let's say, 100 meters. And what does this look like? I want to show you what we did this morning before there was so much people sitting here. This is a 2-minute scan in this room, where you can at least see some people. And what you see here is not a black and white photo. It is intensity coloring of how much laser light that is reflecting from different objects. So here, myself, we can see that obviously my trousers were darker than the skirt. So I will get then a gray scale that is quite similar to a black and white picture. And if we look at the data here, we can see that this is really 3D data. And this is one step. Then, if we should go further on, and we want to really visualize things. We need to do more. And then color is an enormous factor to add to this. So inside those instruments, in this instrument, there is a small color camera that is looking also in the mirror and looking without any parallax error on the surrounding. And those color images can be added to the XYZ data, so we can get XYZ RGB data in every pixel, every point. And I will show you here an example where we scanned an area of Gothenburg out at Götaplatsen. And you can see the instrument here on a, let's say, regular photo. And in the background here is the scan data. Same here, the position of the scanner in front of this really impressive building. And now we'll look at what two persons were capturing for 3 hours. We made 16 scans, so we moved the scanner, different positions around, put it together in one big cloud, and this is what we will be looking at just now. So what you look at here now, you have we are moving from cloud to cloud in one big cloud of 16 times 50 million points. And what you see here is absolutely only points. And you can see some white spots on the ground, and that's actually where the scanner has been standing, because it cannot look down. It has some sort of fixing here. And all this is really scale 1-to-1 in natural as-built documentation. Okay. So this is one way of visualizing buildings, environments. And another area which I want to share with you also, that is industrial scanning, which has been done many years with high demands of accuracy and quality and so on, where we have been working a lot. And here, thanks to those high resolution and color scan data, also paradigm shifts has happened. So if we now look in a welding cell in some sort of factory not far from here, we can see a color scan of some machines. We can see that this is truly 3D data. We can look at it in a small 3D window here and see that, yeah, this is 3D data. And if we then look at it and say that let's compare. Let's look at what do the simulation people or visualization people really work with. Yeah, they are working normally in an environment like this. And if we then try to look at the same area, roughly, we can see that, well, yeah, this is the 3D model of this area. And here we see the scan data of the same area. And really, I would claim that the accuracy and resolution, if you compare, is probably better in the scan area, scan picture here. because you see a lot of more objects. And it's at least correct to the date when it was scanned. So if you should choose, if you were able to choose between the scan environment or the 3D CAD model, I think it would be quite clear that you would try to use the scan data if it's possible to use in the software you're working with. And maybe not even try to update the 3D model in all cases. You could really live with the scan points if the tools are sharp enough. And this is what we want to show you here now. That the software has been developed so long now that even the big software vendors, I was Googling this morning actually, looking at the 3D scan data and Autodesk. And this came up, and this is a seminar Autodesk will have about 3D laser scanning technology and how to use massive point clouds in their softwares. So from 2011 versions of Autodesk, they actually import this kind of 50 million points scan data and work with it in ordinary softwares. So it's a big change. And now I want David to start up your plan and show how this works a little in two different cases. One, the building area with the film, and one industrial application, how you can access the points. So please.
Yes, I'm going to show you two different softwares. First one is called Point Tools, which we use at ATS. So I'm going to start it up. I'm going to import a point dataset of the Götaplatsen, which we saw in the movie. So this is 3.2 gigabytes of scan data. All right, this is 370 million points. You can see it here. Okay. So I'm going to fly around here a little bit.
And this was actually captured some 2 months ago. And the snow in the trees are not from today. And the reason for the snow in the trees, maybe you should explain.
Yes, when it's capturing the laser data point, you get the intensity of the laser beam. But we also do some color capturing using a camera. And then it applies the RGB coloring to the scan points. And when the tree is moving in the wind, you'll get the overlay of the sky on the tree, actually. So this is the sky you see here.
The color of sky.
Color of sky. So this is everything is real-time live. What I'm doing here. It's not a movie.
And then, of course, you can capture more and more data and fill up the environment, so you don't have shadowed areas, of course. But this is just a very quick scanning for 3 hours and some processing for, let's say, half a day.
And there are, of course, lots of tools in this software. I can show you one tool, measuring tool, to really show you that this is 3D data. You can measure between 2 points here. So we'll click on one point here on the floor, on the ground, and one up here. And you will get the vertical distance, which is 13.17 meters. And I can, of course, measure the width of the pillars here, if I want. That's 3.75 meters. And everything is in millimeter, some millimeters accuracy. And I can also click on one single point here to show you the coordinate system. This is the SWIRF coordinate system, and it's, for example, 639, no, 6,000 kilometers from the origin. With millimeter.
Of Sweden, in somewhere.
Yeah, so that's 6 billion millimeters. All right, that's point tools. And another software is called Rhino Zeroes. It's a kind of CAD software, and which we have a plugin, a point tool plugin, to actually load the scan data into the CAD system. And you can see the scan points here and the CAD model overlapping the points. And this model was actually made with help of the scan data. So the model should be really good here. We can look in different views. We have the top view here, for example. And we have this section. I can move the section and see the points moving in this view simultaneously. We can compare and see if the CAD model is correct. You can go to this view. And we move this slider here. And you can see the points are actually moving here. We can compare or model, build a complete model. Okay.
Yeah, so here you can see real life, the tools that can be used for making a 3D model, checking a 3D model, how good it is, or we could even maybe go further on and say that maybe we can live with the points sometimes. I claim that probably you can say that 50% of the projects might be kept in points, and you don't need to model at all. And that will be developed further on during the years. Okay, thanks for us.
All right, thank you very much. I think you showed us greatly how to cut some edges here when we're used to see modelated data, and now we only see some kind of point clouds and working directly in the point cloud mode. I'd like to ask the audience if there are any questions for them. Yes, please. I'll come down with a microphone for you. Nej, vad bra, tack.
Doesn't work.
What's the wavelength of the laser? What's the wavelength of the laser?
It's 780 nanometer.
Okay.
780.
What is the scanning technique? Is it triangulation or is
it's
it?
phase-based measurement for those who see that. So it's phase-based and not pulse.
Okay, thanks.
Which is the two different technologies for long-distance 3D scanning.
I see. Thank you.
May I ask who you are and why you're interested in those questions?
Well, I am an engineer and interested in the technology. Yeah. Thanks very much.
All right, thank you. Any more questions? Yes, Björn, would you please like to give him the microphone?
Yes, I'd like to know about the modeling tools, how to model if you want to create meshes of the clouds. How has that type of tools developed, and if you take for instance the cloud of Götaplatsen, what would be your estimate? What the time is to actually get a mesh out of that place?
Approximately 10 seconds.
Well, short time, but it's different softwares, and what you are aiming for, exactly the result. So we have to compare apple and apple exactly. But there are very efficient software, at least, for that, for sure.
Yeah, of course, you can get one mesh and one object of the whole scene, but then if you want to divide it into the different pieces,
and that's the apple and apple. So we have to talk more detail before you could say a time, actually. But there are very efficient softwares, at least, for meshing. And of course, because they are built during this all rapid prototyping and reverse engineering tools that exist for like say arm scanning and that area, and they are going together here now. So we are using the arm scanning tools that are developed for tenth of a millimeter accuracy, and they can of course be applied here also, and that works nicely.
Are you a software developer?
No, not at all.
Are you a consultant?
I'm a consultant at NCC Technique.
Oh, great. Maybe you have a chit-chat afterwards. Do we have
There's a question there.
We have a last question here, yes.
Yes, hello. My name is Bengt Karlsson. I'm CEO at Meter Architecture here in Gothenburg. How far is this? Is it on the market yet, or?
Okay, it's definitely on the market. It's been commercially used for let's say 10 years in some areas. We have been supporting architects at least the last 5 years, also here in Gothenburg. Especially old houses, 100 years old, and renovating the very top floor to get as-built drawings up there, or as-built data at least.
Are you working with the municipality, the Gothenburg Stadsbyggnadskontoret?
Not exactly, but they should know about this at least.
Yeah. Because I think it's a great benefit if you work with renovating the city, as we shall do now in Gothenburg. We have a huge area, and we have a unique chance because we have an old city, and it's not. We're gonna. I don't know the word, but it's a great ombyggnad.
Yep, sure. Yeah. So let's talk more.
Yeah.
Please.
All right, thank you very much. I have one question for you too, as well. You showed us examples on a building site or at Götaplatsen, and you showed us something from in the industrial environment. Where do you think the market is? Where is the benefits? What's most interesting to go into the areas? Which areas?
I think that it will be used actually very broad, very fast now, because this paradigm shift where the software is so easy to handle. I would say that even the police, for example, or a rescue team, that they could easily have a scanner with them and to a crime site or a crash site or something like that to measure up, document, and get the traffic running again. And that's a massive 3D documentation area. Right. I think even, let's say, architects, in 1 or 2 years, they might even have their own laser scanner, because it will be so easy. You don't, when you're not extremely need the top accuracy you need maybe in some industrial areas, you could probably do it with moderate trained people. And that will explode the area, I think, for these applications.
All right, thank you very much. Is Mr. Magnus Rönning from Volvo Cars. I think Magnus is going to show us how to use these kinds of technology in the environment where he works. Magnus' talk is about assembly plant visualization by 3D laser scanning. Do please welcome Mr. Magnus Rönning.
Thank you very much. Let's see if the computer starts up as it should. I think it does. Yeah, here we go. Let's go back there. My name is Magnus Rönning. I work within the manufacturing engineering department at Volvo Cars with the virtual methods and IT. And I'm here today to introduce you to how we have implemented the technology that Rolf and David just showed you. We are in the midst of implementing this right now. We run a couple of advanced engineering and research projects as we speak, but we also try to implement as we go. So we actually use this technology in the car programs right now. So here is the world of Volvo Cars. As of now, these are our development and production sites. Gothenburg, of course. We build cars also in Belgium, in Malaysia, and in China. We have 2 plants in China, one ongoing and one in production. And we're also setting up a development office in Shanghai. We also have a couple of design departments all over the world, but this is the development and production sites. So, assume that we want to look at the Ghent plant in Belgium. What kind of tools do we have? This is the traditional way of looking at the Ghent plant. This is, or any plant. This is the 2D layout from AutoCAD. The final assembly shop. And down to the right, you can actually probably see the assembly lines and the assigned area for each car here. And this gives you some kind of feeling, and if you're a skilled reader of drawings, you actually know how to interpret this. The other way of doing this is, of course, to buy yourself a plane ticket and go down and see for yourself what it looks like. Much neater way, of course, but it takes time, it takes money. And even though it's definitely possible to do so, if I go down there to see for myself, and I come back to Gothenburg to sit down with my engineering colleagues, the memories that I have from what I saw become distorted even when I'm on the plane back home. And if I were to ask you if the car you saw in the beginning of this movie is red or blue, I would assume that I would have approximately half of you saying it was a red car and half of you saying it was a blue car, because you didn't really pay attention to the color of the car. So if I'm going down there to see for myself, it's extremely important that I actually know what I was looking at and the purpose of that. Otherwise, my memories will become intensely distorted as time goes on. And of course, if I go down there and my colleague 2 weeks ago, and I sit down with a colleague who was down there 4 weeks ago, things might have changed. We saw different things, we looked for different things, and we don't really know what we're talking about when we meet and discuss the future of the Ghent plant. The next option, of course, is to go to 3D CAD, to factory CAD, to lightweight formats such as JT files, and trying to create the structure of the plant, as you see in the middle, and try to organize the entire plant in the work methods that we have with CAD. This is also neat. This is very good for planning, of course. But again, you have a number of problems. First of all, this is a nominal world. So we know that there is a pillar here, but we don't know the exact placement or size of that pillar, because we just instantiate all the pillars of the plant. Also, you have the question of on what level should we do the CAD documentation. The example in the middle, or even the one to the left here, is quite detailed, and it answers a number of questions. But if I'm interested in the installations in the ceiling, for instance, the picture in the middle doesn't do anything for me, because we don't have the CAD, the 3D CAD on that one. And you always get into this kind of problem. How ambitious should I be? And of course, this takes time as well. It's before we're done with the documentation, the plants have changed so much, so it's not really relevant anymore. But this is the future way, and actually at Volvo Cars, this is the current way. So we're looking now at the body in white shop in Ghent, using the technology that you just saw from ATS and the point tool software. Through laser documentation, we have created the huge point clouds of most of the body in white shop and final assembly shop in Ghent, and we're going further with this. So we can actually go down and have this millimeter precision that was presented to you before, and all the details that we need. And this gives you something completely new. You can go see for yourself, but you don't need the plane ticket. You can go see for yourself and see exactly what it looks like, exactly where the pillars are. You can do the measurements that you just saw and have the exact representation of the plant in your computer. So this was the body in white shop, and of course we have the same thing for the final assembly shop. Unfortunately, I've had some problems with this video. I don't know why, but you get the grasp of it anyway. So what we're looking at now is a new way of actually planning and looking at the plant. And we have the 3D point clouds that you just saw, but we also have the Google Street View kind of thingy, where I think it's next week that we get this installed, where we have the overview of the complete cloud to the top right corner, and where we have the complete Google Street View application, so you can just launch it from a web browser and move around in the plant in any which direction you want to. And this is also linked to the point cloud, so eventually we can launch the actual 3D point cloud from this. So the different areas of use here. Of course, visualization is one big thing, where we can go and see during our car programs, when they get developed, what the plants look like, what will be the effects of the new car when we introduce it into the existing plant. And to get the common view, because here we can meet, here we can see the same things, no memory distortion, so we know what we're talking about. We know that this pillar is actually down there, and we know that we have the ceiling installations, so we can't build the high car that we want to maybe without changing the ceiling installations. The second example, of course, is to verify equipment installations. This we have been doing for quite some time in the body in white shop. But of course, with the affordability and the ease of use of this technology now, we can launch this on a much broader scale. And as Rolf also mentioned, we can start looking at a new way of working where we don't actually model everything, but where we model what we need to model and we work in the point cloud directly for the rest. And that's really a paradigm shift for us. The accurate measurements, the millimeter precision, assuming that we want to be in the size race with Audi and BMW. The Audi Q7 is 9 centimeters wider than the current XC90. It's not crystal clear that that car will be able to go through our plant. We have the body window where the body goes through on the assembly line. And if we expand the car with a decimeter, maybe we actually might hit a pillar. We don't have that kind of detail in the drawings, and we don't have that kind of detail in the 3D CAD. But in the visual, in the laser scanned world, we do. Also, looking at the fixture here, which we scanned, we can actually model and model after the scan data and introduce that into our simulation tools, so that we have the accurate data when we do the simulation of the process. And this is actually the example that I was just talking about. If we want to look at a new product in existing plants, this is not a new product. I couldn't show that here really. This is the current XC60. But if we look at the paint shop, for instance, which we also scanned, and see what kind of precision do we have when we go through the paint shop with the car body, it's down to centimeters. And if we have an investigation on a new car, looking at, for instance, a car the size of the Audi Q7, we can instantly now with high precision show what kind of space do we have in the paint shop for that size of car. And this couldn't really be done before in an efficient manner. I always get a number of questions about this. What's the cost? It looks like a very costly way of doing things, but it's quite the opposite. This is very cost efficient for us. Once we have this up and running, there's of course an initial threshold before you get this kind of system and work methods up and running. The cost is about 1 to 2 euros per square meter. So it's a quite affordable way of doing things. If we look at maybe the complete final assembly shop, it's 100,000 square meters. So it's maybe 150,000 euros, 1.5 million SEK. And you can imagine how many CAD resources you could have sitting down and doing the CAD documentation of the final assembly shop for that kind of money. You wouldn't be near completing that drawing. Updating, of course, the model or the point cloud isn't more accurate than the date of the scan. So there will be a constant updating of the point cloud. And also, that's a question, how often can we update? And as we saw earlier as well, this is a very rapid technology. So we're looking at approximately 10,000 square meters per weekend, which we can update. Unfortunately, the plant needs to be standing still when we do the scanning. So basically, we have the weekends. But 10,000 square meters in a weekend, again, that's very, very quick. And the file size, tremendous amount of data. We're talking about loading gigabytes into computers, but we use standard computers. Right now, it works so-so. We are going over to 64-bit environments by the end of the year, and then the problem is solved, really. It's very quick to load in the point clouds, and it's even though the files are huge, it's not a big deal for us. So we're doing this together with ATS, who do the scanning. We use point tools for visualization. KK-stiftelsen helped us to initiate this project 1.5, 2 years ago to get started. And currently we have a EU finance project financed by Eurostars, where we're looking at further developing this and integrating this into our normal work procedures. So that's pretty much what I wanted to show you. Do we have any questions, maybe?
I have several questions. You showed us the Gantt plant. Are there any other plants?
Yes, we have one in Gothenburg, you know.
Yes.
We have one in Chongqing in China, where we produce cars together with Ford and Mazda, and we're currently building a new plant in Chengdu in China. And of course, looking at the expansion all over the world, the plane ticket scenario is really out of the question when we look at China or other remote sites. It's not feasible to go see for yourself with in the ordinary manner.
All right. And while implementing a project like this, which were your biggest challenges to implement it at Volvo?
I would say the biggest challenge is pretty much the one that you brought up during the last presentation. What is the where should we put the focus on this technology? Should it be on the installation of the equipment, or should it be visualization, or should it be the engineering of new products into existing plants? The use of this technology is so broad. So really we need to talk to everybody about everything when introducing this technology. And we already have seen a number of spin-offs looking at the scanning of crash tests and other things. So the technology is so neat and so nice to look at. So the interest is huge. So I could easily spend 40 hours a week just go out and presenting this to all the interested parties. So getting a focus has really been the biggest problem.
All right, and to take the next step then, I perhaps you need some collaboration help or whatever, I don't know.
Most definitely we do. The next step for us is to integrate this with CAD and to understand when do we need CAD and when do we need the point clouds and to find the right level and the right ambition when we're documenting the plant. Because right now we can do so much, but the resources and especially the time is quite limited for us.
Okay. Now perhaps there are any questions. Anyone? Will you stay after this speech?
Yeah,
yes.
Sure.
Can I ask you to stay down by the round table in the far end of this room?
Will do.
And then we could gather up if anyone has any final questions then. All right. Thank you, Mr. Magnus Rönning. And next speech is something completely different, very exciting. It's about 3D capturing, but with other techniques. So please do welcome Dr. Josephine Sullivan from KTH, Royal Institute of Technology in Stockholm. She's going to give us a speech on towards the 3D visualization of football players.
I'd like to introduce myself. I'm Josephine Sullivan. And this work I'm going to present is I've done with people that I work with at KTH in the computer vision and active perception lab. And also we have a industrial partner, TrackCab, and a lot of this work has been funded by the KK Stiftelsen. Is that correct pronunciation? I definitely didn't know how to spell it, but okay. So this is we're going from millions of points or tens of thousands of points down to 12, order of 10 points now. So I hope we can cope. So our goal is from visual data, you want to reconstruct football players or in general, maybe any environment where it's hard to maybe do the scan or you have to have cameras far away, you can't be that close. And why we want to do this besides the academic or intellectual challenge of this is that it's maybe cheaper, less invasive, larger workspaces, and it's easier to take this out to the environment that you want to analyze as opposed to bringing somebody into a motion capture studio. Okay, so this is an example here. in this video here, we clicked on the skeletal joints of the football player, and then using factorization methods, we were able to do a reconstruction. So these are the application domains that we foresee that we could use these, and at the moment, we're focusing more on the middle two, which is the visualization of motion for entertainment purposes and the synthesize of novel viewpoints also for entertainment purposes. So at the moment, what we envisage is that you have lots of cameras maybe on one side of the scene or around the football pitch, and then you do some analysis of the video data, and then you're able to reconstruct novel viewpoints. Okay. So people are doing this already, and you've maybe seen something like this on your telly already. So let's see, we have stop. People move around. They're taken over by a virtual reconstruction of the football. And then, so I think if you watch the Champions League games tonight, you'll see something like this. Okay, so these all look very impressive. And sometimes when you're sitting in your little room in academia, you think, why am I bothering? But these are all very handcrafted. And if you actually look closely, they're only very crudely representing what's going on or what the player is going. Everybody's running in the same way or walking in the same way. Okay, and also they're handcrafted. There's probably a lot of manual tweaking going on to produce this. Okay. So what's not so manual is our commercial partner, TrackCab. They've put cameras around the football pitch, and then they track all the players. So you've probably seen graphics like this that tell you how far player X or player Y have run during the game and where they have been during the game. So I think up until this year in the Allsvenskan, in the Aftonbladet. I presume none of you are reading that, but they used to have these statistics of who ran where and how far. So they provided that data. And this is what they were able to provide in real time without sort of much human interaction. So you can see you basically have dots running around. So this is what you can do in real time on an online application here. Okay. But obviously, even a humble dot wants to be more than they would like to be a Studio Max character. Okay, so I suppose we at KTH we're trying to help in the development from the dot to a Studio Max character. So hopefully we can. We're somewhere in here. So this is what we're aiming towards. Okay. So this is interesting now. So. This is maybe not coming out so well. So what we're seeing here is, this is a video I found on YouTube. This is some fan that took a picture on his mobile phone. This is the same fan going to his Xbox and seeing if he can reconstruct the goal that he saw or he liked on his Xbox, and then get lots of different replays in this. So remember, your Xbox or your Sony PlayStation, they all have lots and lots of canned motion capture data here. So how did he do this? Well, obviously probably lots of manual tweaking. But basically he estimated where the guy taking the free kick, where that occurred on the pitch. Then he probably tweaked around to estimate the 3D orientation of the player's torso with respect to some global coordinate frame. And then he recognized that the player's action, he took a free kick over the wall. And then he probably input this information into the Xbox via his controller. Okay, so in some sense, the visualization is sort of solved, but the recognition is not. Okay, so the human effort was all in finding what the player was doing, estimating which way he was pointing, and estimating where he was on the pitch. Okay, so we want to automate these steps, what the Xboxer did in some sense. So luckily for us, TrackCab have solved the first problem, which is saying where everybody is on the pitch, and we're working towards the latter goals. Okay, which is saying which way is everybody pointing in and what are they doing. Okay. So we have used recent advances in machine learning and techniques like that, basically so that we can isolate where the head and torso are for each player. And then we can grab the image patches around these, around the torso and the head, and try and estimate which way they're looking and which way their torsos are pointing. And then also we can use contextual information, which is where are all the other players on the pitch and where's the ball. So we found that 80% of the time or 90% of the time most of the players are looking at the ball. So that's the look at the ball and then scan around. Okay, but so we're able to estimate with relatively high accuracy. Obviously it doesn't work all the time, but we're getting there. So you can estimate where people are looking and in which way they're pointing, basically. But then the next goal is, if we have lots of training data, so this is the new trend in computer vision, which is solving, doing the recognition problem is hard. Going from visual data to semantic knowledge or to 3D pose is very hard. So you just get lots of label training examples that go from video to the labels, and then you learn a mapping by referring back to your video data or your label training data. Okay, so this is what we're trying to do, is if we have video data and we know which way the person is pointing, can we learn some mapping, which is basically indexing into a huge database to get our 3D pose. Okay, so these methods work really well, but the problem is they don't work so well if you don't have so much data. They basically need you to have mapped out the whole feature space and the whole set of possible 3D poses. So this is where we've reached somewhat of a stumbling block. So this approach where we want to build a qualitative reconstruction, we're assuming that we have access to lots of motion capture data, but unfortunately we don't. And it's costly to obtain such motion capture data from the studio. And also it's not clear to me that you can replicate the whole range of motions from a football game occurring in a real game in an actual studio environment. Okay, so I mean the set of motions that a football player is quite wide. Okay, so how do we? So the last year or two, or a year basically, we've been focusing how can we get lots of motion capture data from real games. So basically, what we've done is we've taken 3 cameras out to real games and zoomed in on one player, and we had three people with walkie-talkies talking to each other and deciding which player to follow, and then zooming on him and following him during a game. So this is just a schematic of what happened here. So hopefully, so this is a game from the end of Allsvenskan last year. So this is AIK, and this is where the player here scored a goal. So as you can see, this is quite challenging to try and build a reconstruction, but we were able to do this. So you can see the cameras are rotating slightly and zooming. So basically we mark the joints manually. So this is the stumbling block at the moment, is that we have to mark most of the skeletal joints manually, but we would like to automate this in the future. So you can see on the far side there, this is a reconstruction that we got. So the really interesting thing here is that even though we only reconstructed 12, 13 points, you still get a very nice feeling of the motion and what it looks like. From the previous talk, I was having sort of a point envy from these large number of points, but it's very interesting that with human motion, you can convey a lot with not so much, but it has to be accurate. Okay, so this is just to show it's the same motion again, but we're spinning around to show that we do in fact have good depth information here. So the thing is, using 3 cameras makes it a lot easier than using 2 cameras or 1 camera. And in fact, we found with just having 1 camera, it's very hard to get accurate results at all. Okay. So. Okay, so what's going to happen in the immediate future is that we would really like to automate this, further automate this process. We would like to really reduce the amount of effort in clicking the joints of the players and then collect really, really large databases of the 3D of football players. In some sense, you would like to create a complete database for every single player that, professional football player. And then use that. That would be sort of an offline process. And then when you have this huge database, you would use this to do real-time or more automated 3D reconstruction. And this would be doing what the Xboxer did, would be you recognize which action is happening, and then you would stitch these all together using on the ground plane, using the trajectories computed by TrackCap. Okay, so I think that's that. Have I any questions?
All right. So. Thank you very much.
Did I go a bit quick? So.
I think we will have several questions now. We're into sports.
Yeah.
Isn't it a sporty audience?
But I think.
Yeah. Well, I have one question. I saw these techniques you are using.
Yeah.
Is it possible for you to borrow knowledge from the other two presenters here today?
Yeah. Well, I'm unclear what happens to these methods when they. There's lots of dynamic motion and occlusions going on. So, this is the major problem. This is why we needed 3 cameras. There's the projections, or you're going from 3D down to 2D, but there's also things are occluded lots of the time. So you would like to see the whole person, at least over the 3 sets of cameras that you have. So.
I think we need to have a talk.
Yeah,
with them.
but it's an ongoing debate in computer vision as well. Point clouds over skeletal models as well. So that's another issue as well. So. Are
you aiming at capturing other sport activities?
Yeah, sure. In some sense, football is quite hard because, as I said, you have it's a team game with a large number of players. So there's lots of occlusions going on all the time. So you can imagine something like tennis. You have somebody who's nice and isolated all the time, so it's much easier in some sense. So, and also the good thing with the tennis players is they're also well trained that all their forehands look exactly the same in their backhands. So that's the.
All right.
These learning methods work much easier. So the range of motions is much less, I think, as well. So.
Now I have given you several minutes of thinking. Any questions for the audience, please? All right. Very well then. Will you stay here afterwards?
Yep. I'm here.
Perhaps you will join us around the table.
Yep.
We will now soon have a coffee break. Thank you very much, Dr. Sullivan. Give her a hand.